In this video, we will pick up where we left off with Chapter 3 on the normal distribution. And I'll start off with a quick recap before we get into the fundamentals of z-scores and how to find percentages from those. But just to do a quick recap, we talked about density functions or density curves. Basically, a density curve is a mathematical function or equation that represents the general pattern that is undergoing a population. Like, for example, a lot of human traits or populations follow this very, what we call a normal distribution, which is shaped sort of like a bell curve, which is why we often refer to it as that. But there are, the primary traits of a density function is that the total area under the curve has to be equal to 100% or 1. And that's because it's the point of the density function is to describe percentages, where it's like if we're talking about what percent of the population has a score lower than this, let's say it's 30%, or what percent of the population has a score higher than 10, and let's say it's 10%. The idea is that the percents, if we add up everything under the curve, it would add up to the total population, so that when we're looking at the full thing, we get 100% all the way through. And that way we can divide it up into areas of our interest to find various proportions that we care about. And so with the normal distribution, just to recap, the two important defining features of the normal distribution are the mean and the standard deviation, which, as we talked about in class, remember, mu and sigma represent the mean and the standard deviation respectively when we're talking about the population as a whole. Remember, when we're talking about a sample, we usually call mean x bar and we call standard deviation s. But we use different variables when we're talking about the population. This is a distinction that is more important to understand later. But for now, that's just what you want to remember. And just like when we talked about these things last week, the mean represents sort of the average, the central point of the data, whereas the standard deviation is a measure of the spread, how spread apart it is. And like we said in class last week, when a standard deviation is small, that means all the data is clustered together. When the standard deviation is larger, it means the data is more spread out. And we can see that with the normal distribution curve, where if it is a larger standard deviation, the density percentages are more spread out. Whereas when the standard deviation is smaller, we get a tighter curve, and it affects the shape. And basically, the mean just affects where is the peak, where is the top of the bell curve, kind of what's the most common outcome, which is usually defined by the mean. And we did a couple examples with the 68, 95, 99.7 rule in order to figure out things like, well, what percent of women would be between this height and so forth. And you can use the standard deviation as a measure of where things are on the curve. And sort of the thing to kind of remember about that is roughly 2/3 of the data falls within one standard deviation of the mean. And then basically almost all of the data, or 19 out of 20, 95% falls within 2. And then close to 100% falls within 30 standard deviations of the mean. And the kind of, this is where we left off in class as well. What if I have a very specific number and I want to know what percent of scores are higher or lower or in between these very particular margins? Because the 68, 95, 99.7 rule is very useful, but it's limited in that it only, it's very specific to the standard deviation. But what if our data is not in increments of the standard deviation? And let's go ahead and take a look at that. So let's start by defining what we call a z-score, and then practice using the z-score to figure out various proportions. In this first couple of videos, we'll just talk about how do you convert it, how do you standardize the score, and then we'll talk more about how you figure out percentages in the next video, or in 1 or 2 videos. But let's go ahead and look at the definition as it appears in our textbook. So it says, if x is an observation from a distribution that has mean mu and standard deviation sigma, the standardized value of x is z is equal to x minus mu divided by sigma. And it says the standardized value is often called a z-score. So let's go ahead and practice using this formula to do a couple calculations and then kind of talk about what this means after we look into this. But essentially, the idea is that we're figuring out how far is our value from the center, and then we're normalizing it based on the standard deviation. And what this will do is it will give us a value like 1 or 1.5 or 2, which is with respect to the standard deviation, which is why we call it standardized. And the term z-score is what most people would refer to this as. It's just another word for standardizing it, but the z distribution is just another word for normal distribution. So if you're wondering, well, why z, that's a good question. But what you can kind of remember is anytime you see z-score or z distribution, that's always just the same things we've been talking about in chapter 3. It's referring to a normal distribution. And so finding a z-score is basically like normalizing that score based on the mean and the standard deviation of the distribution. So let's look at a sample question from the packet. And then the lecture notes should be posted above, and you should be able to find these in there. But let me just go ahead and move to the packet. I believe we completed the first page in class this week. So let's just look at number 4. It says, a U.S. woman is 5'11", and another woman is 5'2". It says, find their z-scores and interpret who is further from the mean. So in class, we looked at the normal distribution of women, and this is not filled in because I'm actually recording this before class. But we approximated the normal the mean height of women in the United States to be about 5'5". And remember, like we said in class, normally real data is not perfectly normal like this. So when we see this sort of distribution, we should take this with a grain of salt. We should not assume this is exactly how women in the U.S. behave, but it gives us a sense of the general pattern at hand. And then we estimated the standard deviation to be about a radius of about 2 inches, because it looked like 5'5" was the central point, and it looked like 5'3" was the mark of the standard deviation. And remember, the first standard deviation can always be seen graphically as what's called an inflection point, the point where the curve switches from getting steeper and steeper to more smooth, which is, you know, kind of where it looks like it's flattening out, sort of. But essentially, that looked like it was about 5'3". And so again, it would be nice to use only inches as we discussed in class for this. 5 feet is 60 inches, so basically 65 inches will be our mean, and that, remember, we refer to that as mu. And then sigma is the width of the standard deviation, which is 2 inches. Sigma is equal to 2. Anyways, we need that in order to be able to find a z-score for women in the United States. And so, again, we're going to assume that is exactly how the distribution of height for women in the United States is. Probably not exactly that, but again, the point of a z-score is to help us understand the pattern if a distribution is normal. And remember, normal, it doesn't mean in English, like normal means kind of average. Normal is very specific in stats to mean bell curve, where the mean is the most common outcome, and things which are larger or smaller are proportionally smaller. Anyways, let's start off with a z-score, and let's just go ahead and mark, okay, the mean was 65 inches, and then the standard deviation was 2 inches. So if we're going to find a z-score for a woman who's 5'11" tall, again, that basically this would be x, and like with our other scores, it would be helpful to convert this to inches. So 60 plus 11, this would be 71 inches tall. So basically, this woman is above average height, and so you know what we'd expect from a z-score. Well, let's go ahead and see what we get, and then we'll kind of talk about what we get from there. So z-score is always equal to, I'll just go ahead and recopy down the formula. It's always x minus mu divided by sigma. And this mathematical structure is very important to the fundamental idea of statistics. We're actually going to be using this all throughout the next couple weeks of class, the same sort of structure where we make adjustments to this formula to change when we're dealing with a slightly different type of problem. But the structure remains pretty much the same. You're taking a difference on the numerator, and the denominator is dividing by the standard deviation now. Anyways, plugging this stuff in, well, her height was 71 inches, and then the mean was 65. So, and the standard deviation is 2. And how we can interpret the numerator is, well, she was 6 inches taller than the average, and that's always what's going to be in the numerator. It's like, what's the value? How much larger is it than average? And basically, when we divide by the standard deviation, we're normalizing that value to remove the variation, because the larger the standard deviation, the larger the spread. And notice if we take that difference, she was 6 inches taller, divided by the standard deviation of 2, what we get is a z-score of 3. And essentially what that tells us is how many standard deviations above the mean was she? Because if we were to go back and look at this chart, basically that woman who was 5'11" would be way over here as a data point, right? As we can see, there's a very small percent of women who would be that tall. Again, assuming this graph is correct, which it probably isn't. But anyways, if you actually kind of look at this, we can see, well, 5'5" was the mean. We would see one standard deviation above would be 5'7". 2 standard deviations above would be 5'9". Notice that 5'11" is 3 standard deviations above the mean. And that's exactly the point of a z-score. It tells you how many standard deviations either to the right or to the left of the mean are you. And that's why we had to divide by the standard deviation to normalize that value. And basically, a z-score will take our score and change it to how far away it is on the scale of standard deviations only. So it gives us a sense of, okay, how far is it away? And remember, one standard deviation means there's a meaning behind that. It means, there's approximately 68% of data falls from one standard deviation. And basically, being 2 standard deviations is pretty extreme. 3 is very extreme. It means it's way above, and it gives us this sort of scalar value. And we can kind of think about it in terms of the general 68, 95, 99 principle. And then also another value of z-score is, well, what if it doesn't fall exactly on the increment? Like the next question is, what's the z-score of a woman who is 5'2" And this would appear right here. Notice that that's actually half of a standard deviation. It's not exactly in increments of 2 inches, because if you're paying attention there, 65 inches was the mean, 63 would be 1 standard deviation below, and 2 standard deviations below would be 61 inches. So notice that certain values, they're not going to be exactly 1 or 2 standard deviations away. A z-score will tell us, in terms of decimals, how far away is it. So let's just go ahead and throw it in the formula and see what we're working with. But in this case, she is 62 inches tall. Again, this is our x. The formula is the same. Our mean, again, mean and standard deviation will not change. Mu and sigma. You need to know that for your normal distribution if you're going to know the z-score. So in a typical type of homework question, they'll give you, here's the mean, here's the standard deviation, figure this thing out. Basically, that's enough information to go ahead and find a z-score. And notice here that she is 3 inches below the mean. Again, if we normalize that score based on the standard deviation, we would get a z-score of negative 1.5. And what this tells us is that she is underneath the mean. She is shorter than the average. And by how many standard deviations? By 1.5. Again, it's not exact, it's not 1 or 2 on, but most scores are not going to be right on the standard deviation marcation. So the point of the z-score is to figure out exactly how many standard deviations away from the mean are you, either positive or negative sense. And later we'll go ahead and talk about, well, how can we interpret a percentage? Like, say we want to know what percent of women in the US will be taller than this, or shorter than this, or whatever. That's all to come. But z-score is fundamental to all of that.